seek and rotation, right? And we had like a sample file. I remember putting a sample problem on there about those.
I think that was chapter 4 or 3.
It was 3.
Neither 3.
Yeah. Okay, so but we didn't go into this little discussion with the architecture, so that's what I want to make sure we covered. Okay, if you're good with that, then we can talk about the sector as far as what does it look like. Okay? Preamble, data, error correcting code. Oh, should have asked any questions? Pretty basic, right? We have to identify that this is sector 1, 2, 3, 4, whatever. It's going to have its data, the error correcting code, so we can do some basic error checks and recoveries. Okay? So now let's take a look at a notional disk while it's actually running. So in this example here, it's running counterclockwise, and it has a numbering scheme like you see here. 0, 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4, 5, and 0, 1, 0, 1, 2, 3, 4, 5. Why do we do that? Why wouldn't we line up 0, 0, 0, 0, 0, 0? Why are we offsetting these zeros? Yeah.
This is a wild guess. Head alignment?
No.
On the platter?
But I'm glad you brought that up because we didn't mention that earlier. So let's say we have a disk system with 3 platters. Okay? If I have a disk system with 3 platters, I then ask the question, are they readable, writable on both sides or just one side of the platter? Most today are double-sided, but not the earlier ones. So most today are double-sided. So that means I can read and write on this one. 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 Surface. I can read and write on this surface. I can read and write on this surface. So in a 3-platter system, I can have 6 disk heads. I have 6 surfaces, right? What I'm going to do is I'm going to take these 6 heads and I'm going to connect them to one staff. Okay? So what this means is that each of these 6 surfaces, I'm going to have a disk head positioned above it at the same track. They will all be at the same track at the same time. Okay, and this thing is spinning really fast. And I've got these disk heads here that are going to be all on the same track at the same time. So one of the things that we recognize is that it takes time to read these bytes. And while we're reading these bytes, this thing is spinning. So if I want to go from track 0 to track 1, it's also going to take time, even if it's a tiny little bit of movement, it's still going to take some time to move it from track 0 to track 1. Okay, so if I'm reading sector 0 on track 0, and I want to shift to sector 0 on track 1, my disk is moved, right? So instead of putting 0 immediately adjacent to this 0 on this track, I'm going to skew it. I'm going to say, in most cases, I'm going to go from 0 to 0, but the disk has moved. So instead of putting zeros, stacking them all up on the same sector, I'm going to offset them or skew them so that I can gain some efficiencies. Make sense? So when we talk about track skewing, that's what we're talking about. Let's place those addresses at different locations because we recognize most of the times we're only going to go from sector 0 to sector 0 to sector 0, but between tracks. While we're at it, I'm not done with this thing yet. Okay, so all the heads are connected to the same arm, which is connected to another arm that moves the heads to whatever track I want them to be over. Okay? This is a voice coil. Those are heads. These are arms. Okay, so we're going to use the voice coil to drive our heads, which means that it's undergoing a couple of things. It's going to accelerate, it's going to reach maximum velocity, and then it's going to decelerate. All of that, it's a latency, it's a specific latency, it's called seek time. And it's both mechanical and electrical, right? Because the voice coil itself has to warm up, position, accelerate, hit maximum velocity, decelerate to get it exactly over that track.
Is that why they throw like those neodymium magnets in there, or neodymium magnets? Is that for like for the coil, coiling system?
No, the coil has its own flux that it's generating here. It's just a copper coil.
Well, I mean, electrons going through, that's
Yeah.
flux, yeah.
Creating a flux to move this magnet.
So what are the magnets are for? Like those strong neodymium magnets they have like inside like mechanical drives. I've always been interested.
Talk about that outline.
Okay.
What else? So that's seek time. What we were trying to do with skews, using our cylinder skewing, what we're trying to do is reduce what we call rotational delay. This is another component of our latencies, rotational delays. Because what's happening, if I put myself over whatever track I want it to be, I might be over cylinder 0 right now, but what I really need is cylinder 14. Okay, once I get positioned here, I have to wait until 14 is underneath the heads before I can read it, right? That is rotational delay. And so the cylinder skew model here is trying to reduce the amount of rotational delay by saying, hey, if I'm already reading a particular cylinder from a particular track, it's very likely that I'm going to read that same cylinder from another track, and I'm just trying to reduce that rotational delay by doing this skewing. Okay, so when we talk about cylinder skewing, we're trying to decrease rotational delay. And we can explain why, right? Got it? Okay. Okay, another way we can help reduce delays, even cylinder, specifically rotational delays, is take a look at the way we format our disks. Now, off the top of your head, you're thinking the same thing that most people think, and that is, okay, it's number 0, 1, 2, 3, 4, 5, 6, and 7, and that's a pretty easy way to divide it up, and you're right. It is a pretty easy way to divide it up. It's just not a very smart way to divide it up because of the fact that we have different cylinders that we have to read at different times based upon the fact that not every instruction read that I'm going to use is contiguous, right? I might read a block, which might be co-located in one sector, and then I might need to go another block, which is somewhere else. So, or I may need to do a head reposition, in which case there's a delay. So in those scenarios, it's best not to have these numbered consecutively. Okay, so what we do instead is we come up with this interleaving scheme, right? Where in the case of straight interlacing here, interleaving rather, I simply go from 0, skip 1, 1, skip 1, 2, skip 1, 3, skip 1, 4, skip 1, 5, skip 1, 6, right? And that way, if those delays from doing my data transfers, okay, be accounted for by skipping over one sector. And then I can get the next one, and then the next one. Likewise, if I'm going somewhere else, I really want it to be somewhere else. Okay, so interlacing was good. But then, as we got more analysis, more data analysis that we did on how these reads were happening with the hard drives, we said, yeah, but sometimes it's harder because of systems are double buffering, or it's not double buffering rather, but they're longer in their processing time to move bytes across the signals, that we needed longer delays. And so we came up with a double interleaving scheme where we said, okay, 0, but now instead of skipping 1, we skip 2. So 0, 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 2, 4, 1, 2, 5. Okay, so that gave us more time between sectors moving underneath the heads than we had before. The other thing that happened that sort of drove us to this technology here is our good friends over there in the CE department figured out the way for these disks to spin real fast. Okay, so as we increased the rotational speed of these disks, a single interleave wasn't enough. Okay, so we need to introduce more delay because we made it go faster, right? As well as some more randomness in the blocks that we're trying to transfer. That was another reason for double interleave. Got that? Interleave, double interleave. You can do the addressing. Yeah, it's not that hard. All right, so some basics. Read write, the disk head must be at the desired track, at the beginning of the desired sector. Seek time. We talked about that, right? Need to accelerate, get to speed, decelerate, put those heads over the sector you want. That's seek time. Rotational delay, time it takes for the sector to reach the head, which we talked about. So the other thing, seek, rotational delay, is the data transfer itself. Like I was mentioning earlier, it takes time for the head to sense or write the byte or bytes to or from the planner across these wires, and from these wires the signals go into the controller, right, the disk controller. Which is also forming all these signals to move these, and the timing to get it over the right place, all that good stuff. But it'll also take those signals and it will form bytes from those signals. And from those bytes, it'll form individual bytes for a stream-oriented transfer, or a collection of bytes for a block-oriented transfer. Right? So this controller is going to do all that in addition to recognizing whether that's a 1 or a 0. Okay, so we have the data transfer rate, that's what we're talking about just there. Rotational delay, seek time. Okay, that's the latency of I/O transfers in a disk. There's this thing called access time. It's the sum of seek time and rotational delay, getting this thing in the right position, and then we could calculate the data transfer separately And we can also calculate the total transfer time. The total transfer time is this formula here, where we have number of bytes. Total transfer time is equal to the number of bytes divided by the revolutions per second times the number of bytes per track. And the idea is to minimize or maximize the transfer time.
Minimize?
Are we trying to minimize or maximize the transfer time?
You definitely want to minimize that.
Yeah, you wouldn't minimize it. You want to go as fast as possible. You want the lowest number possible, right? But that's how you determine it. Number of bytes you try to transfer, divided by how fast the thing's spinning, the number of bytes per track. Questions? Just performance. Another little fun fact I should mention. Disk reads versus disk writes. When you're doing a disk read, you're doing exactly what we've been describing so far, and exactly what you probably think. When that particular sector track byte is under the head, I can then sense it with the head, and electrically I can determine whether that's a 1 or a 0, depending upon if I'm spinning left, spinning right, or however I design my 1s and 0s for this disk manufacturer. Okay? So it senses it, and it can determine if it's a 1 or a 0, the disk controller can. To do a write operation takes exactly twice as long. Because what will happen first is it's going to write to that byte. So we gotta wait till we gotta do the whole rotational delay time, or maybe the seek the rotational delay time, to we get the right byte under the head, and then I can write that byte. In other words, I can spin it left or spin it right, depending upon what that disk manufacturer says is a 1 or a 0. And then I wait for it to come back around again, and I read it. And I compare the two. Because sometimes the writes don't always work. So disk writes will always take at least twice as long as any read. It might take more, because we have found that sometimes when you're changing the spinning direction of that 1 or a 0, it doesn't always fully happen. And so you have to do another write operation, and then you're going to read it again to make sure it worked. Once you've done that, then it's a successful write. You can go on to the next job. Okay? Makes sense? SSDs have that problem?
No, it's all good.
Solid states never have that problem?
Avoid,
The spinning of magnetic flux?
no.
No. There's no magnetic flux in SSDs, right? Right. Sometimes that flux is just a little stubborn, right? CE friends, are you guys playing with little tiny pieces of flux in your CE labs?
I don't want to think about physics.
We have some CE students amongst us here. I was just curious as to whether you're playing with tiny little pieces of flux. No? Okay. Yeah, when I was talking with my friends over there, they were saying the same thing. Yeah, we don't really do that much anymore. It used to be a lab where we would set up like little tiny part of what would be on a disk, and then we would play with just how much energy and how much time you would have to spin that energy to get these things to spin and stick. It was kind of a fun little experiment. Anyway, I kind of thought we moved on beyond that. Okay, error handling. Sometimes parts of disks go bad. Right? Anybody experienced the disk go bad, parts of it or all of it? Yeah. True confessions. Yeah, sometimes they happen. Sometimes they happen a little bit at a time, and we have some routines in here, some bits that we've set up to manage this so we can gracefully let a disk degrade and continue using it without panicking the poor user. Okay? Which is a good thing. We like it when we don't panic the users, because then they keep buying our stuff. right? So when we format our disk, we're not going to give all of the sectors to the file system. We're going to predict in the future that some sectors are going to go bad because we have numbers that show it. Lots of analysis, lots of data has been studied. We know this happens. So we'll save some sectors in case some of our sectors go bad. So in this example here, I only saved 2, which is kind of silly, but it's an easy example to show. Right? So I saved 2 sectors as spare sectors. And at some point here, I recognize that one of my sectors has gone bad. How do I know that? Well, that's a whole other class. But we determined that one of them went bad. Some number of bytes would not stick and work, and we're getting bad returns. I could never get a successful write in this sector. Okay, so after some number of tries, I determine that's just a bad sector. I flag it as a bad sector, in which case I mark it as bad in the file system itself, and the file system's address for this sector number 7 now becomes one of my spares. So in this case, sector 30 is now virtually my 7. So anytime I try to get to address sector 7, I will go to sector 30 instead. Okay? So is it possible to actually move sectors around on the disk so I can just keep it at address 7? Instead of doing this virtual renumbering thing? Couldn't I just move this sector from here to here? No? Why not?
Isn't it just the physical property of
Yeah.
just got that location?
That's a physical sector. It physically sits right there and it's physically bad. Right. So no, I can't just pick this one up and replace it. So I have to come up with this mark and renumber scheme. Okay. So you're saying, okay, enough about disks. Okay, USB drives, that's the way of the future. These things are gonna be around a long time. There's a lot of them out there, they're really inexpensive. Yeah, they're going away, but it'll be around for quite a while still. Okay, so it's good to know these disk systems because maybe you're gonna go out there and ask to build device drivers for them or come up with some better addressing schemes or some ways to optimize your data transfers and stuff like that. So yeah, it's important to know this stuff still. Right? Okay, let's take a 10-minute break here. We'll come back and talk about clocks and fun stuff. So